Hello and welcome to week 9. This week we are going to look at the tree data structure. My name is Mildred. Up until this point we have looked at different linear data structures. We have seen that data are arranged in contiguous memory, that is in a sequence or next to each other. We've seen linked lists, we've seen arrays, we've seen stacks and queues. All of these are linear data structure, and we have data and then we know what the next position is for the next element. But in the tree, every node can have more than one pointer. So when we have a node, it can point to or branch out at different paths. That is what we call a tree. It is non-linear. It's a hierarchical data structure consisting of nodes, and these nodes are connected by edges. So these are nodes A, B, C, D, E, F, and the edges are these lines that connect these nodes. Now the first node here is called the root node. It's the topmost element in the tree data structure. Now that root is a parent to a left child and a right child. This left child is like a left subtree that has its own children, so left and right, and then this right child has just one child. Now this child that has no child is called the leaf node. So any node you see that is like the end that has no child is the leaf node. When you see this line that goes from the root to a leaf node, you count it 1, 2. You can look at another line that goes here, 1, 2 lines. You can come this way, 1, 2 lines. So the maximum number of lines from the root to a leaf node is the height of the tree. So in this case it's 2. Assuming we have another line coming here, then we'll have the height is 3. Alright. And so when you want to see the height of a node, that is how you count it. Then the size of a tree is the number of nodes. So 1, 2, 3, 4, 5, 6 is the size of the tree. When you want to talk about the height of a node, it's the same thing like the height of a tree, but you just focus on that node like this, and the height here is 1. Okay, so we know the different terminologies that are used. Let's look at the different types of trees. We have general tree, in which every node can have any number of children. Then we have the binary tree, where the maximum number of children, like what you see on your screen here, is 2. So you cannot see like a third child for this tree if it's a binary tree. Then we have something we call the binary search tree, BST, where the left node or the left child here is less than the parent and the value of this right is greater than the parent. That is a binary search. Then we have a full binary tree where every node has either 0 or 2 children. We have a complete binary tree where all levels are filled except the last level that will be filled from left to right. Then we have a perfect binary tree where all internal nodes have 2 children and all leaves are at the same level. And we have the balance tree or the AVL tree. We're going to look at that in details in week 10. Now let's see how we can implement a binary tree in Python, and let's try to manually construct this tree. So let's use a class, and we'll call this class node. The init method will have property that is the data. So when we create an instance of this class, we want to supply a node. So we can call it data node, whatever you want to call it. So let's say self.data is equal to the data, and we want to have the left node, self.left is equal to, we'll set this as none, and self.right, we set this as none. Now this is all there is to creating it. Let's manually construct this tree here. So we have the roots. So let's name this root, and this root is equal to, we create an instance of the node class and it is a, the value is a, so we'll pass that in. Now the root has a left, so we'll say root.left. So let's come here and say root.left is equal to, create an instance, a new instance here, so another object here is b. It has a right, that is c, so we'll say root.right is equal to node c. Now we're done with the roots and this first level, left and right. Now this root.left, let's come to this child now, root.left. This root.left has a left child d, so the left of the root.left is equal to node d, and then we have the right of the root.left, so say root.left.right is equal to node e. Now the child of this AC, the right child, so the root.right has only a right child, so root.right.right, which is equal to node f. So we have manually constructed this. But how do we traverse through a tree in Python? The traversing is just a process of you visiting all the nodes in a particular order, and there are 2 different categories. We have the depth first traversal, DFS, where we visit the root down the tree branch by branch like this. So we'll come to the left branch, we'll visit everything at the left, and then we'll come to the right, visit everything at the right. So we'll do that until we get to the leaf of each branch. And there are 3 types of depth first traversal, where we do pre-order, where we go from the root to the left and go to the right. We do in order, when we go to the left, do the root root and the right, and then we have post order where we do the left, the right, and then the root. And so we are going to create functions that we are going to use to illustrate this. The second category is the breadth first traversal, BFS, where it's like a level order traversal where you go level by level, like you're going sideways like that. We're going to look at that also. So let's start with the depth first traversal, and let's try to create a function that we can use to do pre-order traversal. So let's say def pre-order, and we want to have the root as the argument. Now the algorithm is to visit the root first, then we traverse the left subtree, and then we traverse the right subtree. So we want to use recursion for this. So I want to say if root, so if a root is supplied, we want to print out the root. Let's print out root. So let's say print root.data, and then the end will be a space so we can see it, or we can put an arrow for us to see how to traverse here. Then we want to recursively call the pre-order to do on the left subtree, and then repeat it on the right subtree. So we'll say pre-order root.left, and then pre-order root.right. Okay, and so when it's coming to the left subtree, it will print out the root and all the children there. Do it recursively until it gets to the leaf. Now let's do the in order traversal, def in order. Now for this one, we know that we want to go left, root, right. The algorithm is to traverse the left subtree, then visit the root, and then traverse the right. And so let's say if root, we want to cursively call in order on the root.left, and then we want to visit the root next. So we're going to print root.data, and let's put an arrow for the end, and then we will do visit the right. Now for the post order, let's say if root, we want to visit the left, so we'll do post order root.left, we visit the right, post order root.right, and then we print or visit the root. So just copy this. So you can see how we use recursion to do this for all three functions that we have. Now we can test this and see how it traverses. So let's print. I'm going to print let's say pre-order traversal, and for this one I will just print out pre-order root, because we already manually defined all of this or created them. So we run the pre-order function there, and I'll do this for in order and post order. Let's see what we get. In order traversal, in order root, and post order traversal, post order root. So let's run this and we can see how it displays. Sorry, I'm supposed to comment this out. It's commented out. This is supposed to be well commented out, so it's printing out there. But we can see from the pre-order traversal, and we have A, B, D, E, C, F. That's for pre-order. We have this, we have that. So this is basically it for pre-order, for in order, for post order traversal, like that. So we have the pre-order root, we have the in order, we have the post order. So if I just use print and have them, and it links to the last none because it's done. Alright, because these are the leaves. Now we can see that there is none at the end. So we have seen how we use these different traversal types. Let's look at the breadth first traversal, and we can implement this using a queue to visit node level by level. And let me delete this. I'll leave this node class, and I'll delete all of this. And let's say I say def level order, and if not root, I want to return. Then I want to use, let's import something in Python. We call this, so from collections module. So from collections, we want to import the queue. And so if you go to the collections module, you see what the dequeue function or method does. Okay, so we're going to use that here. So let's say queue is equal to dequeue, and we want to dequeue the root. Now while queue, we want to get the node will now be equal to, we want to pop left, right, because for queue it is first in first out. So queue dot pop left. So what we're trying to achieve here is once it has visited a node, we just want to keep going, right? So pop left, and then we'll print out node dot data, and let's say we want the end to be, let's use an arrow. Then we want to see if the node is a left node, we want to append to the left, and if it's a right, we want to append to the right. So we'll say if node dot left, then we want to say queue dot append node dot left, if node dot right, queue append node dot. So we've created this function that we can use to illustrate or implement the level order traversal, or the breadth first traversal, where we go like sideways. So when we do this, let's try to run this. Let me say print, and I want to use level order root and I pass in the root because we already manually created it here. And so when I run, I have the structure. When it's go side by side, sideways for each level, it will start with the root A, then to go to the other level B, C, then to come D, E, F. So we'll see it A, B, C, D, E, F, and then that's the end after it. So this is the level order or the breadth-first traversal implementation. So we've seen how to implement all of this. Join the live web conference on Saturday for us to look at real-world implementation or a real app implementation for this tree data structure. Next week we're going to go deeper and look at the balance tree, and then we're going to look at how we can do the array implementation, and we're going to look at the binary search trees. Thank you and see you next week.